Hey guys, today we are starting chapter 6, which is all about exponential functions. That is our next different type of function. We'll get into this chapter, how they are used, what scenarios and what real life applications they are or there exists for exponentials. But before we get into that, we have to talk about kind of the base operations for exponentials. And as you could guess, the word exponentials has the word exponent in it. It's its base word. So exponentials deal with exponents. So for 6.1, for this first set of notes, we're going back to some basics and just looking at exponent rules. A lot of this stuff you should already know, that you guys covered it in middle school, exponent rules. So this should be more of a refresher for us, just to make sure we remember how those exponent rules work, and then we can go ahead and start applying those as we get into later sections. So before we get too far into it, I just want to remind ourselves of some vocabulary, some phrases, so that you guys know and I know when I say a base or I say an exponent, or sometimes we could call it the power, that you know what I'm talking about, which number I'm referring to. So this is an exponential term. It has a base and it has an exponent. So here this is 3 squared is how we would say it out loud, or 3 to the second power. My base is 3. That is the number that's being multiplied. The exponent is 2 here. That tells me how many times I'm multiplying that base together. And that's basically what an exponent does. It takes this base and multiplies it together a certain number of times. So the most common one we've dealt with is squaring something to the second power, which is just multiplying it by itself. So 3 squared being 3 times 3 would be positive 9. So what we're going to be doing today is looking at 3 different rules of how these terms could interact with each other. So we'll look at what happens when I have 2 exponential terms multiplying together, 2 exponential terms dividing one another, and then what happens if we have an exponent being raised to another exponent. So to start with here, we're going to look at what would happen if I have 4 to the 5th power times 4 squared. So we'll take this kind of slow and step by step first, and then try and figure out a shortcut for it. If I were going to take 4 to the 5th power times 4 squared, I would have to literally write out, because 4 to the 5th power is 4 multiplied together 5 times. So that's this first set of 4s here. 1, 2, 3, 4, 5. Times 4 squared would be 4 times 4. Right? 4 squared being 2 4s. So I could write this as 4 to the 7th power. Now, we should be able to try and work backwards then and figure out a shortcut on how we could get 4 to the 7th power without having to expand this all the way out. And to do that, if we take a look at the base, we know the base is 4 in both of them. That is very, very important. These exponent rules that we're going to be looking at only apply if my base is the same. So because these are both 4s as the base, then we can look at these exponent rules. So in total, there are 7 exponents. Right? We have 2 distinct exponents, but if I were to add them together, I get 7, right? 4 to the 5th power, 4 to the 2nd power, 5 plus 2 is 7, which, hey, that seems almost too convenient that my answer ended up being 4 to the 7th power, which is our shortcut. If you have 2 of the same bases being multiplied together, all you have to do is add the exponents. So without having to expand stuff out, we can do this next problem. 9 to the 8th power times 9 to the 3rd power. My base here is positive 9. How many are there? Well, there's 8 in the first, 3 in the second, so there are 11 total exponents, right? Those are my exponents on 9. So the way that I would usually show my work here, you don't have to necessarily write those answers in every time you're doing these problems. I would rewrite 9 to the 8th power times 9 to the 3rd power as 9 to the 8 plus 3 power, which gives me 9 to the 11th. And that is my answer. Just for myself, when I'm at what I would expect you guys to simplify and what you can leave as an exponent, basically if either your base or your exponent is 3 or smaller, I would expect you to write it as a single number. So here, I'm not going to make you write out what 9 to the 11th power is, because it's a huge, massive, ridiculously big number. Same thing with 4 to the 7th. You could do 4 to the 7th on your calculator and figure out what that number is, but I'm fine with leaving it as 4 to the 7th. Because again, neither the base nor the exponent is a 3 or smaller. All right, so if we get into this next one, my next one's a little bit trickier because I've got division, I've got a fraction, both of which are kind of scary for some of us. But again, we'll do it the old-fashioned way first. So we've got 7 to the 6th power over 7 to the 3rd power. So if we expanded this all the way out, we'll write 7 6 times up top and 7 3 times in the bottom. Right? 7 to the 6th power over 7 to the 3rd. Well, we can look and see, all right, we've got common 7s on both top and bottom. So you can already see I cancel out 1 pair, 2 pair, 3 pairs, and I'm left with 7 times 7 times 7, which I could write as 7 to the 3rd power. Now again, that doesn't come from nowhere. We're going to try and figure out what the pattern is. So if you look and see, my original exponents were 6 and 3. So I'm trying to figure out, right, how could I use 6 and 3 to get my answer of 3? Well, in this case, the answer is subtraction. 7 to the 6 minus 3rd power gives me 7 to the 3rd. So what that looks like and kind of where that goes, this is the one where it's a little bit tricky, and the notes that we'll do after this section, 0 and negative exponents, hopefully will help clarify that, but for right now, we'll at least have a good enough base to get started with these. So looking at kind of the answers that I've gone through and already have filled in here for us, my base is 7. The exponent in the numerator, so how many 7s are there up top? That's the numerator. There's 6 of them. How many are in the denominator? Well, there's 3 7s, 7 to the 3rd power. So if we subtract them, 6 minus 3 equals 3. And in this case, because kind of what I call the leftovers, which is that 3 after I subtract them, we know that they go up top because there were originally more 7s up top than there were in the bottom. So here, since I started with most of my 7s up top, the leftovers go there, right? Because I'm only subtracting 3 off of that group, and I still have those other 3 left over up top. So if I go ahead and take a look at this next one, 12 to the 4th power over 12 to the 7th power, what is my base? All right, well, my base is 12. How many are in the numerator? There's 4 of them. How many are in the denominator? There's 7 of them. So if I subtract them, 7 minus 4 gives me 3. But in this case, my leftovers, that 12 to the 3rd power, will go in the bottom because I started with more 12s in the bottom than in the top. So I ended up with 1 over 12 to the 3rd power, which that I would expect, just like I probably would up here as well, being 343. Since it's a 3rd exponent, I would expect you to simplify that all the way. I'm going to move this over here a little bit to make some more room because it's a little bit of a bigger number. That gives me 1 over 1728. So what that'll look like, and again, this next step that I'm about to write here will make a little bit more sense tomorrow after we do the negative exponents. But the way I would write this up, 12 to the 4 minus 7th power, which gives me 12 to the negative 3rd, which means I have to flip that over. Again, we'll explore that idea in much more detail, at least for the general idea for simplifying exponents. For division, this will suffice. All right, one more example, and we're going to skip over the questions over there. We're going to jump right into the meat of the problem. If I've got 9 to the 8th power over 9 to the 5th power, well, okay, I've got my same base. I'm going to subtract my exponents. 8 minus 5 gives me 9 to the 3rd power. I know that 3rd power stays up top. My leftovers stay up top because I originally had 8 9s in the top, so I had more up top. So 9 to the 3rd power would be my answer, but that is an exponent of 3, so I have to make sure I simplify that down to just a single number and get 729. That now, I guess I just probably should go through that part with you. All of your calculators are capable of doing exponents, and whatever calculator you end up using, I can help you figure out what buttons you need to make sure you're pushing for exponents. Most of them, at least the ones that I have in my classroom, have this little, it's called a caret button. It looks like a little rooftop, if you were trying to do 9 to the third power, you would type in 9. It looks like that. And then 3, and then hit equals. It would give you 729. Some calculators, the button looks like this. It's a little like X to the Y button, X to the Y power. That tells you that first thing you type in is your base. The second thing you would type in would be your exponent. So you would type in 9, that button, 3, and then hit equals. And again, it should give you 729. So play around with whatever calculator you're usually going to use, whatever you're going to use on a quiz or a test, so that you make sure that when you do 9 to the third power, you should get 729. So if you need to pause it real quick, grab your calculator and test it out, because if you can't evaluate with your calculator for different exponents, this whole chapter is going to be really, really difficult for you. So I want to make sure that you guys can do that now. And if you do have questions and can't figure it out, again, let me know. I'll be able to figure out what button looks like. Sometimes the order is a little bit different, so again, you have to play around with it, because here 9 to the third power is 729, so that's what you should be getting. If you get something different, it might be that you need to flip the order of what you write stuff in. Some calculators are weird like that. All right, on to our third and final relationship here. So this one is a little bit different because we don't have two bases. We just have a single base that we're dealing with. But we have two exponents that we're dealing with. So that's what makes these a little bit unique. I have an exponent being raised to another exponent power, which means if I have 3 to the 4th power and that is squared, this is the same thing as saying 3 to the 4th power times 3 to the 4th power, because we know that squaring something means multiplying that base together twice. And if what's inside this parenthesis, 3 to the 4th power, is being multiplied by itself, right, 2 of them, that's what this translates to. So 3 to the 4th power times 3 to the 4th power. So that's how we would go about expanding that. So I got my first group of 3's, my first group of 4 3's, times my second group of 4 3's. And we can see in total, we end up with 3 to the 8th power. 3 to the 8th power, because we've got 4 in that first group, 4 in the second group, 8 total. Now again, most of us probably recognize what that pattern is if we're trying to figure out how we can use my exponents to get my answer. Well, if my exponents were 4 and 2, and my end answer is 8, well, 4 times 2 is 8. That is my pattern here. So if I have an exponent being raised to another exponent power, you just multiply those exponents. That's your answer. So if we try that with this next one, 7 squared to the 5th power, I would just rewrite that as 7 to the 2 times 5 power, which gives me 7 to the 10th. And that's it. 7 to the 10th power. All right, so that is all 3 of our different exponent rules. Those that we've been dealing with here are just numbers. What we're going to get into next here is going to be how we interact with, or how we deal with them when we have both numbers and variables. Now again, the important thing to remember is that for all of these problems, my bases were the same. Anytime I can use these rules, it's only when my base is the same. So here, I both had a base of 4, base of 9, 7, 12, 9, and then my exponent rule with power to another power, I have just a single base, so that one obviously we don't have to get those to match up. But with all of them, I have to be dealing with that base, because it gets a little bit more complicated when we start mixing both coefficients and variables together. So how we end up dealing with this, I still can use these same exponent rules on the things that are the same base. So here in this first problem, when we have variables and numbers mixed together, my x in both of my two terms, are the same base. That x is the same. So I can use my exponent rule on that. But my numbers, I just have to follow whatever this operation is. So if I multiplied 2x to the 3rd power times 5x to the 6th power, I know that multiplying those two coefficients together would give me 10. Right? 2 times 5 is 10. And then for my x's, since they're the same base, I can follow that exponent rule, because I have 9 of those in total. I just add them up, just like I did up above. So if I go ahead and just jump down into that rule with this next one, 11r to the 7th power plus 3r to the 5th, I would just multiply my coefficients together, 11 times 3. And then for my r value, I'm just going to add my exponents, just like I did on the very first problems we did. If my base is the same, I can just add the exponents when they're multiplied together. So in total, I would end up with 33r to the 12th power. 33r to the 12th power. Okay. Let's go ahead and jump into division problems. Division, again, a little more complicated because now I have a fraction or two numbers to divide, and then worrying about also my subtraction rule for what we'll eventually call my quotient rule. But it's still dealing with them as two separate things. I focus on one thing at a time. I first start with my coefficients. So that fraction 9 over 3, I simplify that down and reduce it as far as possible, just like as if it was a fraction that I was dealing with. So in this case, 9 over 3, that would reduce to a positive 3 over 1. 3 over 1, 9 over 3, they both are divisible by 3, so I'm just reducing both of them, dividing top and bottom by 3. That's how I'm doing that. And now we go back to our rule that we used before. If I have the same base and I have them being divided, I would just subtract my exponents. So I've got 4 minus 3 is 1. My leftovers, I'm going to rewrite this here. My leftovers have to go in the bottom, y to the first power, because I started with more y's in the bottom. Right, I had 3 up top, 4 in the bottom, so that's where my leftovers go. So 3 over y to the first, or just 3 over y, would be that final simplification. Okay, so for this next one, I've got 6w to the 5th power over 7w squared. So I'm going to, again, look at my coefficients first, 6 over 7. If that reduces, I'm going to reduce it. If it doesn't reduce, in this case, it doesn't, I'm just going to leave it as is. I'm going to leave it as 6 over 7. That does not change at all. Now my variables, my w's, they are the same base, so I can apply that same exponent rule. I can take my exponents and subtract them. 5 minus 2 is 3. Those leftovers would go up top because I had more w's up there to start with. Right? 5 is bigger than 2, so my leftovers go where the 5 was. So 6w to the 3rd power over 7 would be my final answer for that problem. Again, when I'm dealing with coefficients and variables, coefficients, you just follow the operation, division, multiplication, whatever it is, and then we use that exponent rule on our variables because they're the same base. All right, getting into our power to another power. This one gets a little bit more complicated as well because now I have two different things inside my parenthesis. So if I was going to go ahead and say I'm expanding this all the way out, I have 5z squared to the 3rd power, which means I have 5z squared times 5z squared times 5z squared. Because that exponent of 3 all the way on the outside tells me that everything inside my parenthesis gets multiplied together 3 times. So that means I have 1, 2, 3 5s that I'm going to be multiplying together. And then z squared, I've got 3 pairs of z's. So z times z, z times z, z times z. They each just get the exponent of 3. So that's the shortcut of doing this. If you look at inside my parenthesis, each of my two things, my coefficient and then any variable, I'm just applying that exponent of 3. So that's the shortcut here, is recognizing that 5 to the 3rd power is going to be my new coefficient, because it's 5 times 5 times 5. 5 to the 3rd power is 125. And then for my z squared to the 3rd power, that's where then we go back and apply that exponent rule. So again, if I have an exponent being raised to another exponent power, we can just multiply those together, and that's how we get z to the 6th power. So let's go ahead and jump in here and give this one a shot. So the way that I would rewrite this one, I would say this is 3 to the 4th power, and then k to the third power to the fourth power, which I'm forgetting how I would usually do the shortcut. I can just know, I know that I'm going to be multiplying those together. So 3 to the fourth times k to the 3 times fourth power, which 3 to the fourth power is 81. K to the 12th. 3 times 4 being 12. All right. So let's go ahead and summarize here. So this is our way of writing up our exponent rules. Just kind of summarizing what we do with each of these different things. These are what we call them. So when we have a base being multiplied by the same base, we call that product rule because my bases are products of each other, right? They're being multiplied together. So our product rule is when we have the same base being multiplied together. In that rule, if we have both variables and bases, I would multiply the coefficients. Right? In this case, 7 times 4 gives me my 28. So I multiplied the coefficients. And then for the exponents, I add the exponent. Right? X to the third times x to the fifth gives me x to the eighth. 3 plus 5 equals 8. For the middle one here, this is what we call our quotient rule. Quotient being the fancy term for what the answer is when you divide. Right? Quotient means division. So in quotient rule, with our coefficients, you can call this one of two ways. We're going to go ahead and divide the quotient or the coefficients, or we can say we're going to reduce them if it's a fraction and it doesn't divide perfectly. We're either dividing or reducing our coefficients. And then for our exponents, we're going to subtract those exponents. Right? 8 minus 2 being 6. Our third and final rule is called power rule. That is because we have a power being raised to another power. Not very creative, but we have no other operations going on for how our exponents are being applied. So that's why we call it power rule. So in power rule, remember, for our coefficients, for those numbers out in front, we're going to go ahead and raise to a power. So I guess we could say raise to our outside power. So here, 8 is just going to be raised to the second power. 8 squared gives us that 64. And then for our exponents, we are going to go ahead and multiply our exponents. So z to the third power squared, 3 times 2 being 6. That's how we get z to the sixth power. Now, this is if we have both variables and exponent, or variables and numbers, coefficients. This far right table, the far right column, this is what we do. This is what we would use if I only have bases. So you're going to have some on the homework, or I guess if I only have a base. So on that first page that we did, where we had numbers just being raised to an exponent power, that's where I would just look at this. So if I have two numbers being multiplied together, I would add their exponents. If I have two numbers being divided by each other, I would subtract their exponents. If I have a number being raised to a power and then another raised to another power, I would multiply those two exponents. You don't have to worry about what you're doing with the coefficients because there's no coefficients. All right, I'm going to do just a couple of these. I'm not going to do every single one of them just because it's already about 20-ish minutes into the video. And a lot of these are just another example. We'll just pick out one of them. So let's just do, I don't know, like we do the odd numbers, I suppose. So for these odd numbers, again, look at what rule we're using. So what's our operation between our bases? Here for number 1, we have multiplication in the middle, so we should be using our product rule. Our product rule tells us that we're going to multiply our coefficients, so negative 12 times negative 3. And then for our base, we're going to add those exponents together. So I should end up with positive 36 x to the 13th power. Negative 12 times negative 3 is a positive 36. And then 9 plus 4 is 13. So 36 x to the 13th power. For number 3 is 7v to the 4th power, and that is all being squared. This is our power rule, right? We have an exponent being raised to another exponent, a power to another power. So in that, we are supposed to raise our coefficient to the outside power, the outside exponent. So 7 is going to be squared. And then for our base, we're taking our exponents and multiplying them. So this should give me 49v to the 8th power. 49v to the 8th. And then for our last one, our last odd here, for quotient rule, right? We've got a fraction, we've got a division happening. For quotient rule, we're going to go ahead and reduce our coefficients. 5 over 2 does not reduce at all. Now, the subtraction here for our next step, because we're supposed to do our base exponent minus our exponent, right? 9 minus a negative 3 is actually very tricky because I have to subtract a negative. So we have to remember that subtracting a negative is actually like adding. So what I end up with here, our leftovers, is actually bigger than either of the two original ones because we're adding that number because we subtracted the negative. So the way that I would write this, I know that 9 plus 3 is 12, and that leftovers still goes with whichever one was bigger to start with. So in this problem, since my h to the 9th power was up top, that's where my leftovers go. So the way that I would write this up, I would say 5h to the 12th all over 2. Because my 5 and my 2 didn't reduce at all. They didn't have anything in common, or they don't have anything in common. So they stay just where they were. My 5 stays up top, my 2 stays down below. But my h's, I can combine those together and say that this is h to the 12th power up top. All right, that is all I got for you guys today. Your homework for this section is a worksheet. It should be in the packet that you guys have. It's also posted on Google Classroom for those of you who are remote and don't have the hard copy yet. As always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. And have a fantastic day. We'll see you guys soon.